Okay, hello everyone. I'm Kelly. I'm currently a UKI Future Leaders Fellow and a Senior Lecturer in the Department of Computer Science at the University of Exeter. Today, I would like to share with you our recent work on the effect of automated parameter optimization for cross-project defect prediction. Here is the outline of this talk. First of all, I will give you some background knowledge related to defect prediction. Then I will go straight to the methodology used in our empirical study and therefore the results and analysis. So when we are talking about a defect in the software testing, it is an error or a bug in an application. I think it is very natural that a programmer can make mistakes or errors when they build a software due to various reasons. For example, like a deadline for the new version or something like that. Well, actually, software defects are disasters to a software company and our society. As stated in the latest edition of the Software Fail Watch from the Transcendence report, it is reported that software failures have led to around 1.7 trillion US dollars. Therefore, it's very important to help software managers to identify high defect software modules in order to prioritize the actions in the software development life cycles. So in recent years, due to the explosion of machine learning and artificial intelligence, it has become increasingly prevalent to use machine learning for software defect prediction. However, one of the biggest hassles is the data used to train a high-quality model is not as sufficient as you expect, especially when you are developing a brand new project or you are in a startup without many experience. Cross-project defect prediction has become increasingly popular as an effective way to deal with such shortage of training data. Its basic idea is to leverage data from other projects to build the model and apply it to predict the defects in the current project. So in this case, transfer learning is a powerful tool to achieve this purpose. So everything sounds so good, but the machine learning is not really like the magic box we expect. Normally, there are some parameters associated with the machine learning algorithms. The setting of them can largely influence the performance of prediction accuracy. As stated in some recent work, 87% classification techniques used in defect prediction are with at least one parameter. From our statistics, 85% widely used CPDP techniques require at least one parameter to set up in the transfer learning stage. In this case, you can see that why someone called machine learning as academy instead of science. So in this paper, our major purpose is to validate or to use a series of empirical studies to validate how automated parameter optimization or machine learning models can impact the performance of CPDP. There we go. Let's go to our empirical methodology. So basically, we have 6 rules to follow in order to pick up the datasets for our purpose. At the end, our datasets consists of 20 open source projects with more than 10,000 of instances. In order to optimize the hyperparameters of transfer learning algorithms and classifiers, we use a state-of-the-art software package, HyperOPT, as the parameter optimizer. And this is the architecture of our automated parameter optimization framework for CPDP. Here we use AUC as the performance metric. 8 transfer learners and 8 classifiers are considered as the baseline of our experiments. Since model training is usually computationally expensive, so we assume that computational budgets is limited with the 100 or 1,000 function variations, which means that for a particular parameter, we will train the model for like 1,000 times. So each optimization is repeated 10 times. So, alright, let's move on to look at our results. In our experiments, we are going to address 3 research. First one is about how much benefit we can have when we optimize the parameters of defect prediction models in the context of CPDP. So it is worth noting that since we have two independent parts in CPDP, one is the transferability and the other one is the quantification, so we can essentially have three types of parameter optimization methods. The first one is to optimize these two parts simultaneously. The second type is to only optimize one part alone at a time while keeping the other parts as default. The last type is to equally distribute the cost to both parts. So in order to present the results, we investigate the magnitude of the AUC achieved by the parameter optimization rather than the raw AUC values. In particular, we use the coherent Defects to quantify such magnitude. So from the results, so what you can see is very clear. 10 out of 13 existing CPDP techniques have been improved substantially after parameter optimization. So you can see that the parameter optimization works. So the second question is the follow-up with the first one. Since we have 4 different optimization methods, so which one is the most cost-effective one when we have a limited computational budget? So here is the results. The bar chart tells us the percentage of significantly better performance achieved by the type 2-1 method, which is the best, and it is interesting because this type only focuses on the optimizing the parameters associated with the transfer learning, while the parameters associated with the classification are kept at default setting. And here is the volume plots of the different CPDP models. So in the world, these results are very interesting, and it suggests that the transfer learning part is more important in CPDP. The last research question is to challenge the current integration we have with some CPDP models correctly by our data. So, but obviously we can distribute some of the new ones by combining different transfer learners and classifiers. So whether the ones developed in the literature are really state of the art. So in order to address this research question, we have made up combinations of those transfer learners and classifiers. Finally, we built like 62 effective CPDP models. 30 of them are already existing in the literature. So for the better visualization, we only present the top 10. And we also used some non-parametric statistical tests to validate the difference of the results. So here is the results. We just give a few. The black charts represent the existing ones, while the white ones are those newly developed ones. So what you can see is like the newly developed ones are always better than the existing ones. And here is another overview of the results. So what you can see like our newly developed CPDP models are at least as good as the existing. So here is the summary of the findings in this paper. So first, the parameter optimization works. Second, optimizing transfer learning part is cost effective. And last, the current CPDP integration is far from mature. So the source code used to implement our implementation can be found from our GitHub repository. So at the end, I would like to appreciate the hard work from our wonderful collaborators. Ask any questions.